Yes, perfect. Thank you. I think that means it's waking up. Yeah. Well, at least everybody can hear my cough very well now that I have the mic. Okay, now let's see whether that means that mine no longer works.
Obviously.
See, I'm sure now you just killed my connection.
That was the whole point.
Exactly.
Good morning, everyone. Welcome to the last day of the workshop. I hope everyone recovered from last night. I guess half of you.
I guess not everyone recovered.
Where is Brad?
So, do tell what happened last night.
I know. I was abandoned at the dinner. So that's fine. And Brad told me he's going to sleep, but apparently he won't morning.
Okay.
I think most of the people that are staying in the hotel are not. Awesome.
Sadly, it looks like I will need one more minute because HUJI did kill my connection. It worked perfectly fine until I let you try yours.
No, not this thing again. So it worked on the TV screens, but not on the main screen.
Oh yeah.
We've been in this movie.
Yes.
So it's not the connection because it's working over there. Yeah.
Oh, it might be the connection because it's, oh, did touch something here maybe.
Oh, maybe I touched something. Okay.
I don't know.
Oh, I'm sorry. Right screen, left screen, projector.
Projector on. And it is on, of course. Let's see.
Or in the projector making business.
Let's try this through.
Your computer one, wait, is it on screen? RGB.
Oh, there it is.
Okay, I don't know what you did, but it's now working. Thank you.
All right.
Okay.
So our first speaker is Ilya. Go ahead.
All right. Thank you very much. I apologize in advance if I have to cough profusely during this talk, but it seems that Jerusalem is a place that sort of gets under your skin in more ways than one. So thanks to everybody who managed to brave the hangover and still show up today. I will try to talk about the tidal disruption of binary stars. And this is work that was largely done with Yuri Levin from Monash. And now there is a graduate student from Birmingham, Ben Bradnick, who has also become involved in the second phase of this work. This is not the plot that was supposed to come out. Okay, wonderful. So here we have a nice binary. So this is Yuri at the top and me below, and we're trying to, be a nice, happy binary, sort of dance around each other. But there's a little bit of a problem here because Yuri, from what I hear, is a terrific tango dancer. And the only thing I can dance is salsa, and rather than being terrific, I'm pretty much terrible at it. So that means that as we are dancing our happy dance as a binary, we really, we can't really stay in the same place. We keep on bumping into things, as bad dancers tend to do on the dance floor. So we bump into other stars, into other binaries. Sometimes we bump into maybe some molecular cloud, or we bump into an intermediate mass black hole, or something else. And that, of course, means that we're constantly changing our energy and, in particular, angular momentum, as Tal has told us yesterday. And that means that pretty soon we find that instead of just dancing somewhere far away from any danger zone, well outside of certainly the sphere of influence of any black holes, we find ourselves getting a little dangerously close to a mean black hole over there. And of course, you know what happens next. The standard picture is that we get tidally separated by the tidal forces of this black hole. Perhaps I get captured by the black hole, get stretched, eventually tidally disrupted, and fall in. Perhaps Yuri is a little bit more lucky than me and is instead ejected as a hypervelocity star, going off at several hundred kilometers per second or more. Okay, that's the standard picture.
You don't get ejected, you don't get swallowed by the black hole so quickly. I mean, you just get captured.
Sure, you get captured, right? And eventually, if you may continue to walk around in angular momentum space, and eventually you right, indeed. So first you're just in the loss cone for binary tidal separation, and then perhaps you make your way into the loss cone for individual stellar disruption. Absolutely, the difference is that essentially, it's a question of the size of the binary versus the size of the star that determines which loss cone you're in. Absolutely, Tom. But consider the following situation. What happens if we are really quite far away, as I said, perhaps starting out at a radius beyond the sphere of influence of the black hole, and then we are certainly very much in the full loss cone regime, meaning that a single unlucky perturbation to our orbit somewhere at apoapsis very far away, where we spend most of our time and where we have such a huge lever arm because we're on such a large period eccentric, nearly parabolic orbit around the massive black hole, that a little perturbation out there can really very significantly change the closest approach that we have to the massive black hole. We're scattered directly into the loss cone for not just the binary tidal separation, which is denoted here by the dashed blue lines, but for the tidal disruption of individual stars. So you might say, well, this is surely extremely unlikely, but not necessarily so unlikely, because if you actually consider, for example, the fact that it seems that Opic's law more or less holds, and binary radii roughly look like they're uniform in the log, and for massive stars, if anything, they look like they're more concentrated at small separations. We actually have a non-negligible fraction of binaries which have radii that are only a few times larger than the stellar radii, right? Where the stars are not so far away from Roche lobe overflow. And certainly for those things, there isn't a huge difference. It's maybe an order of magnitude, maybe less, in the size of the loss cone for the tidal disruption of a star and the tidal separation of a binary. So suppose we're scattered over here directly into this loss cone for the tidal disruption of a star. So what happens then? Well, what happens then is that, of course, we're still initially tidally separated. That happens first. But then we essentially follow almost the same trajectory, because the angular momentum that the center of mass of our binary has around the massive black hole is still significantly larger than the relative angular momentum we have as relative to each other as part of a binary. And so now Yuri and I find that really, yes, we're tidally separated, but then we follow nearly the same trajectory around the black hole. And so we're now going to be sequentially tidally disrupted. One of us gets tidally disrupted first, the other one follows shortly thereafter. So now we have a possibility for a double tidal disruption event. Okay, I said that this is not so incredibly unlikely. We actually did some numerical calculations using Hannah Rain's rebound package, basically just integrating the trajectories of binaries drawn from some reasonable distributions of initial orbital separations, initial masses and mass ratios, initial eccentricities, and evolved them as they were perturbed and in some cases ended up coming too dangerously close for their own good to the tidal disruption loss cone. And we indeed found that a non-negligible fraction of these binaries ended up having double tidal disruption events. So here there are a couple of histograms, one as a function of the periapsis of the binary center of mass relative to the massive black hole in units of solar radii, and you can see that when the binary comes too close to the massive black hole, double tidal disruptions are overwhelmingly favored. Of course, if the binary stays happily far away from the massive black hole, then usually this is what we call an uneventful encounter. In blue, nothing much happens. There are a few cases of single tidal disruptions, this light blue color in the intermediate regime, so it can happen, of course, because, for example, even though our stars may follow a fairly similar trajectory, but suppose that our stars have very different masses and therefore different radii, it can happen that one of the stars gets tidally disrupted and the other one doesn't. Also, there are some possibilities for tidally induced mergers, and I'll discuss those in more detail later. Also, here's a plot showing what the behavior is as a function of the same major axis of the binary, and again, as you might expect, smaller same major axes generally prefer these double tidal disruption events. They're less likely as you go to larger same major axes.
These fractions can be estimated analytically. In the full Oscon case, it will be roughly the ratio between the separation of the two stars to the radii.
Exactly. Exactly.
And in the empty Oscon, it turns out to be not so different from that. It's just a logarithmic correction. This is somewhat of a surprise because you would think that in the empty Oscon things diffuse and they only hit the tidal radius from the outside. But strong scattering can actually bring them also deep into the tidal radius and bring the result which is not that different from the empty Oscon.
So the next question you might ask is, could we actually have any hope of, if there is really double tidal disruption, of being able to tell whether or not this is somehow different from just a single star being disrupted? Is there any hope of having a special signature here? And let me say up front that we have not done any hydro simulations. I'm in fact very much hoping that somebody would become interested in doing one. But all we have looked at was just the mass return rates, m dot, without considering anything about the interaction of the tidal streams either with themselves or with each other. But you might just simply ask yourself the question, what is the sort of typical separation between, let's say, the peak times for the mass return rates, or they're sort of the presumed peak of the luminosity as estimated using this very simple prescription saying that luminosity is just directly proportional to m dot. And we find that in general the separation can be, at least in some cases, of order the typical size of the peak itself, and that the in most cases because the stars are roughly of comparable size in a significant fraction of the cases, we're using essentially a uniform in the mass ratio initial distribution. It means that the mass return rates are also likely to be fairly comparable, so the two peaks are going to be of a comparable size. So just to give you a little illustration, here is what using the prescriptions from James's work, here is what the behavior might look like just adding together completely independently two peaks from the tidal disruption of one star from the tidal disruption of another star. In this case, actually, it's not so much the difference in the tidal disruption times that matters as the difference in, just due to the size of the differences in sizes of the two stars, the difference in the time between nominal tidal disruption, the time when you get to the tidal disruption radius, and the peak of the mass return rate, basically the time when the most bound ejecta make it back. And you can see that, okay, this is a 10 to the 6 solar mass black hole. There's a difference of order of a month. In this case, of course, it would be a much larger difference for more massive objects.
You're assuming that this figure that these are two completely independent events.
Exactly. And this is clearly not the right thing to do. Here's a little visualization. This one is actually courtesy of James. So I passed on a couple of our dynamics simulations to James, and he plotted what he thinks the ejected streams would look like. And you can see that in some cases the ejected streams essentially are non-interacting. So you can see this here. This is a sort of 2D plot in the orbital plane. This is a 3D plot, but with one of the axes artificially enlarged to make things more visible. But in this case, you can see that there is clearly interaction and self-intersection of the two streams, and this happens even before you get you return to periapsis. So in other words, there's going to be a lot more interaction going on here, and this could, of course, very significantly change the potential circularization timescale, could very significantly change the overall light curves that you might expect to see from this kind of an event. So Rem, I completely agree with you that the right thing to do would be to, in fact, try to model what happens using, let's say, some sort of an SPH simulation, what happens with the interactions of the streams. One thing to keep in mind is that usually, precisely because the angular momentum around the massive black hole is more significant than the delta L due to the orbital angular momentum of the two stars around each other, we find that typically the orbital planes of the two ejecta streams are going to be very similar, and even the eccentricity vectors are going to be very similar, right? You can see this over here. You can see that there's a little bit of a difference between eccentricity vectors here, but really not much in both cases. So the eccentricity vectors are typically aligned, and I think in only one out of 1,000 simulations that we had done did we see a case where the orbital planes were very significantly different from each other, misaligned by more than 90 degrees, right? In most cases, the orbital planes are a few degrees away from each other. The eccentricity vectors are a few degrees away from each other. So that means it's not going to be a case of something completely wild happening, but absolutely there's going to be some interesting stuff going on here, and I think it would be very interesting to look at this in more detail.
I actually have I didn't think this before this hearing your talk, but I have a very different picture in my mind of what's going to happen. I don't think it's going to look like this for a typical case, because I think if the separation between the two stars is somewhat larger than their own sizes,
Yes.
has to be, then one of the tidal springs is going to be completely unbound. It's going to be tidally disrupted, but all the material is going to be unbound, because the spread in the energy within the star is going to be smaller than the spread in the energy between the two stars. And the other one is going to be something like this. So one of the debris, I think, is never going to, from one of the stars, is never going to return. All of it is going to be lost in a typical case. And the other one, all of it is going to be a creep.
Sorry, I don't understand this argument. So I don't understand why, by the time the two stars are, we're talking about the stars being tidally disrupted, right? The binary has been tidally separated. The stars don't know about each other and don't care about each other, right?
But
So
they each differ from the parabolic orbit, the nominal parabolic orbit that they both came on, by a significant amount, which is comparable to their separation, not to their size. So one of them is going to have overall positive energy, and one of them is going to have overall negative energy, like the hypervelocity star separation. One of them is going to be bound, the other one is going to be ejected as a hypervelocity star. Now, because both of them came very close to the black hole, both of them are going to be disrupted. So the one that should have been disrupted was a point mass, a bound object, will be one of your ellipses plotted in here. And the other one that should have come as a hypervelocity star would be a disrupted hypervelocity star, but none of its material is going to come back.
So I don't think that actually happens. It may happen in some small fraction of the cases. I don't think it happens regularly, but let me actually check on that. So that okay, that's a very good suggestion. Let me check on that.
Actually happen in the majority of cases, and I was thinking about this when I cleared this before, that it's only in the phase when the velocity is
Right.
perpendicular.
What I'm
to the
suggesting
path,
will happen in the
you don't
majority
get
of the
the
cases.
ring
That's what I
in general.
It's not entirely unbound, right? The spread in energy is only 8,000 kilometers per second from the most bound to least bound degree. The typical hypervelocity star velocities are 2,000 to 3,000 kilometers per second. So at most, you'll have a larger unbound fraction, but you still have some bound degree in both double tidal.
I don't see how this would be, because the spread in energy is proportional to the separation. The separation within the star is proportional to its radius, and between the star proportional to the separation between the stars.
It's not, it said it's the tidal radius of the thing that you're destroying by time, right? So for the binary, you cross the tidal radius first, the stars cross their tidal radii deeper in.
Yeah.
So the EP plunging encounters of the binary is actually tidally destroyed before the stars are. The only time it would be similar is when they're a contact binary.
Yeah.
So that's why the energy spread across the binary is smaller than the energy spread across the individual stars.
I mean, I'm considering an extreme case. Suppose I took my binary and I tossed it at the massive black hole so that it really, the center of mass of the binary was going straight into the massive black hole, right?
Yeah.
Right? Then, okay, clearly, whatever little perturbation I have on top of this, right, from the binary moving around each other, both stars are going to be, obviously, will end up being tidally disrupted, right? And they will both be fully bound, right? So I don't think.
No. Suppose there are 2 point masses which you throw readily into black holes. When they come out, if they come out, one will be a hypervelocity star and the other one will be bound. They can't be both bound because then you'll have negative energy.
The center of mass orbit hits your
Yes.
Right? And now it's the question of the spread of the energy compared to the mean energy of each of these objects, which is a question James tried to address, but I'm not sure his conclusion is right. Okay, I don't want.
Okay. Yeah. Let me think about this. Okay, that's a very good point. Let me think about this. Thank you. Okay, so I just wanted to say that maybe there are some unusual tidal disruptions, just to provide a little bit of a justification for this. I'm not saying that this is necessarily these are indications that what we are proposing here is really happening. So here is a recent result from Merloni et al. And maybe that you see something that looks like a sort of t to the minus 5/3, roughly speaking, fall off, but with a second peak over here, just maybe. This one is actually from work by Group 8 also. This is work that Stephanie and Richard had done, and I think Stephanie had already mentioned this event during her talk. So this is a situation where something like 20 years later you had a second transient event coming from the same system that was initially identified as a X-ray tidal disruption source. Now, one of the possibilities here is that, for example, if this is what we identify as single tidal disruptions, in some cases, of course, in practice, the orbit is not exactly parabolic, and what can actually happen is that the second star does eventually return, but returns on a orbit which is brings it back towards the massive black hole, something like on average 10 to 50 years later, and so these are the kinds of events that we might be potentially seeing if there's a single tidal disruption of a binary but followed by the tidal disruption of the other companion. The other interesting possibility, of course, is what does this say about the famous jetted tidal disruptions, like this famous event that we've heard so much about from Swift. And of course, one of the interesting possibilities here is what about the systems that actually got merged by tidal forces? The binaries got merged just prior to possibly tidally disrupting the merger product. So here, of course, one of the big questions is how do you get sufficiently large magnetic fields or magnetic fluxes in order to power prompt jet formation. And for Sashchikovskoy and colleagues, for example, argued that you need a magnetic flux of something like 10 to the 29 Gauss centimeter squared in order to power this prompt jet formation. So where do you get such a big magnetic flux from? And one of the possibilities maybe is, and I know that there are people who disagree with this in the audience, but one of the possibilities may be that if you actually have a binary merger, then as a result of this binary merger, you end up possibly enhancing the magnetic field in the remnant by essentially winding up the magnetic fields in the process of the merger. And so you may have a star with a very significantly enhanced magnetic field, and maybe when you tidally disrupt that merger product, you now have a much greater reservoir of magnetic field or magnetic flux to power prompt jet formation. And let me just mention one last thing. I realize I'm basically at the end of the time is, this was all about the full loss cone events. What happens in the empty loss cone? And the answer is that in the empty loss cone, you actually have, I'm going to skip a couple of slides, but you have quite a, this is work that we're doing right now with Ben Bradnick, a Birmingham grad student, and we see that, and these are very preliminary results, but we see that there are quite a few tidally induced mergers that happen in the empty loss cone regime, and of course some of these objects will go on to be tidally disrupted again, so it may be that quite a non-negligible fraction of overall tidal disruption events are in fact tidal disruptions of fairly recent merger products. Okay, and given that I'm at the end of my time, I'll just post these conclusions and stop here. Thank you.
That's a comment on the mergers. To check whether you get much more of them in case we start using client binaries. Because we saw in papers with Fabio Antonini that you could actually get these mergers because of Kozai during the info. So just check it. I would suspect that many of the mergers are those with highly inclined.
So we are doing simulations at all inclinations. I don't have actually a plot as a function of inclination, but you're absolutely right that inclination plays a big role. So one thing that you can, sorry, I'm going to show the two slides I skipped in response to Hagai's talk, so Hagai's question. So here we're just considering actually there's no evolution here of the binary's angular momentum in the next two plots, the binary's angular momentum relative to the massive black hole. All that we're doing is we're just launching the binary multiple times on the same parabolic orbit with a periapsis separation of something like 4 times the binary's tidal separation radius, right? And as you might expect, if you look at the same major axis or you look at the eccentricity, there are little fluctuations. This is the point where the binary happens to fly right by the massive black hole. Then we just compress the part when the binary is very far away, right? This is, okay, I call it parabolic. Suppose it's an orbit with an eccentricity of 0.9999, right? So just so I don't have to continue to calculate the trajectory when nothing is happening, I'm just gluing the passages onto each other, and you see that, okay, nothing much is happening. There's a little bit of oscillatory behavior at a level of 1 over the periapsis divided by tidal separation cubed, but no secular growth. And then in some cases, you see things like this, and indeed inclination has something to do with it, but it's not just inclination. But you see that over here, yes, these are the passages where we fly by the massive black hole, but you see that, for example, for eccentricity, right, we see something that looks like actually something almost like secular evolution, even though these are just independent flybys. And you can see, for example, over here, eccentricity has gone up from 0.92 to basically nearly 1. So this means that a merger is extremely likely at this point, for example. This is the eccentricity of the inner binary, just to be clear. Rem?
I think I'm taking my comment back, because I think indeed the larger the separation is, the smaller the spread in the energy, and therefore the spread in the energy within each star is going to be larger. So I think that figure is not accurate because you don't show the unbound stuff, and there must be some of it, those two rings.
Right.
Oh, yeah, okay.
So the unbound
Yes.
stuff is missing. But
Yes, there is no unbound stuff in that, right,
but
absolutely.
That both of them will be returning to the black hole will be right. I don't know, did you think about it more, Phil, or?
Well, I think that what's missing in your argument, what's the binary type of stuff to make it, the two stars then get gravitationally close to as they go in, so the separation is smaller when they get to the stellar type of structure than they get to one when they enter.
Right.
So at that point, you can then apply the usual argument to it. So
I can also apply the usual argument from the beginning. The
Yeah,
energy
you
can
do it
both
both ways, I think.
is GM over the size times the mass ratio to the
Oh, yes, I'm sorry.
So the mass ratio to the 1/3, whether I take 1 star or 2 stars, it's all the same. GM over A is smaller for the binary than for each star separately. So
I would look at the,
right.
I would look at it differently. Effectively, second, the companion does have higher velocity. It doesn't call it orbit. But so that's the biggest bound, but it's still telling you
This,
something.
oh,
Okay.
this is the right colors?
But that was the one
Oh.
whether it
No, it's on the screen like that. as
Maybe
well.
it's a flux thing.
No, so I agree that because
if they're
the
not
less
bound,
you
Here,
be
give me
less
one second.
bound, and then the difference
or
is
not
not
bound at all.
Have this.
Oh, yeah.
There we go. Disable.
What the hell is this?
Yeah, something weird. Yeah.
And then just because of the coincidence of stage, so they kind of have a smaller effective radius for some fraction of stuff. So it could be a case that some fraction of stuff in the velocity spread similar to the spread. So I would guess at least most of them.
I tend to agree now.
Let's continue over coffee. Our next speaker is Jamie.
Hi, I'm Jamie Law-Smith. I'm a first-year graduate student at UC Santa Cruz. I'm going to talk about the tidal disruption of helium core white dwarfs with hydrogen envelopes, as well as how these fit in to the tidal disruption menu of the possible menu of tidal disruption events. So first I'm going to address what helium white dwarfs are, what they look like, so that we're all on the same page. Next I'll talk about this tidal disruption menu, and by that I mean which stars, which objects we can disrupt by which mass black holes, and where the helium white dwarfs fit into this picture. And then I'll talk about some of the hydrodynamic simulations we've done of helium white dwarfs. So first, the helium white dwarfs. We could think of them as being formed in a binary interaction where a regular white dwarf, its growth is interrupted through a common envelope evolution. And what you get out in the end is a lower mass white dwarf, so less than about half a solar mass, with a degenerate helium core and an extended hydrogen-rich or almost entirely hydrogen envelope. And this is going to be the important point here, is that these things can be extremely more extended in radius than their cold white dwarf counterparts. Here's the extremely simplistic picture of what's going on. So we have they're formed in close binaries, and you can have a number of different primary and secondaries, but the point is that one of them will evolve into a giant or supergiant or subgiant, and then you'll have a common envelope evolution, which I won't go into here. And what you're left with is as I said, a smaller helium core with a more extended hydrogen envelope in just this kind of very simplistic picture. And you have a small hydrogen burning layer that surrounds the core. And depending on the initial masses of the binaries and depending on the initial masses of the binary, you can get a very different picture here with the ratio of the radius of the envelope to the radius of the core. The salient point here, what I want you to walk away with, is that the envelope, as I've been stressing, is much more extended than the core. And it does this with a very little amount of hydrogen. So the mass of hydrogen is typically less than 1% of the mass of the core. So you have a very tenuous extended hydrogen envelope attached to an essentially inert helium core white dwarf. And so you effectively increase the size of this thing by by a factor of a few without increasing the mass. Now I'll talk about the tidal disruption menu. So part of the motivation for this is, and I think something that people were excited about with TDEs, is the ability to probe intermediate mass black holes, because we don't really know the occupation fraction of these very well yet. And today I'm going to focus on a particular region right around here where I think that helium white dwarfs might give us a bit of an advantage. And I'll argue, broad strokes, that main sequence stars are not circularized effectively here. The cold white dwarfs are too dense to be disrupted here, but that these helium white dwarfs with hydrogen envelopes can fit the bill for disrupting and circularizing for these mass black holes. So when we're thinking about the tidal disruption menu, we care about basically where an object can be disrupted. And this depends, I'm going to talk about two very easy things that this depends on. First being stellar structure, that is the mass-radius relationship, and the second being the black hole spin. And in fact, what I'll show you today just neglects the black hole spin. We just take A equals 0. So the stellar structure comes in with the mass and the radius for the tidal radius of the object. So for our helium white dwarfs, the mass doesn't really increase from an inert white dwarf, whereas the radius we can get an enhancement of 2 to 5, depending on how much of the envelope has burned, as we'll see. So this kind of helps us out here. And in terms of the black hole spin, we know that different spin black holes allow material to get closer before being fully disrupted. But I'll just take this simplistic condition here for disruption. We just want the tidal radius to be greater than the Schwarzschild radius. And so what does this give us for different objects? And I'll look at a few. So we have the mass of the object along the y-axis, and the x-axis is the mass of the black hole. And so the mass-radius relationship of these different objects should give us a picture of where the boundaries lie in this space. And the boundaries are going to be where the tidal radius is equal to the Schwarzschild radius. So for main sequence stars, they look something like this. Evolved stars get are less dense and can therefore be disrupted at higher mass black holes than main sequence stars. And so they can fill in this section here. Sorry, that's a little bit tough to see the shading there. Cold white dwarfs are much more dense than either of these, and so they live in a kind of lower regime over here, as we see. And so these lines are where the gravitational radius, where the tidal radius is equal to the Schwarzschild radius, and they're just determined by the mass-radius relationship of these objects. And then if we think about planets and different composition planets, they kind of live down here. So this is a very simplistic picture, and one thing we can think about immediately is where things might be circularized a little more efficiently. And we could take the naive assumption that circularization occurs when the tidal radius is less than a few gravitational radii, so maybe 5 or 10. So with 5, we get this restriction in phase space. This is for strong circularization. It only occurs for these black hole masses, for the different objects. And you might notice a little bit of a gap here. This is a bit of the motivation for this project. Before we fill in that gap, we have to think a little bit more about the helium white dwarfs. So they have this hydrogen envelope, but it doesn't stay there. It burns over time. And this is just a cartoon sketch of what you might expect for different mass hydrogen white dwarfs. For the less massive ones, they burn their hydrogen envelope much more slowly. And so they'll have hydrogen envelope that's still a factor of more than 2 of the core for gigayears. Whereas as you get into the larger mass helium white dwarfs, and we only ran a few models, so we'd like to explore this phase space fully. But this is, I think we ran 4 different models of white dwarf mass in MESA. And for more massive ones, the hydrogen envelope, first of all, the total radius starts out smaller, and then the hydrogen envelope is basically its biggest before 0.1 gigayears. So it has a very, very short-lived puffed up phase, and then it slowly declines. And this is just an example of the, cut off there a little bit, of the evolution of, I think this is for a 0.15 solar mass white dwarf with hydrogen envelope. And you can see how extreme, how long the hydrogen envelope persists. So the axis here is log base 10 of age over years. And maybe I'll just try to, just so I'm not cut off for other things, I'll try. No, okay. And so we see this is the radius over here. The radius persists for 10 gigayears. So the hydrogen burning lasts for a long time in these objects, which is pretty exciting because they're extremely extended here. The radius of the cold, so this is the total radius, and the radius of a cold white dwarf is not even on this axis. So it's much smaller. This is more than a factor of 5 larger. And over here, this is just the helium content. So, is that right? Yes, the helium content.
When you say
Yes.
core of the radius of the white dwarf, you mean the radius of the actual dense core?
No, I mean
Puffed up because it's hot, or
I mean the total radius of the
why,
object.
why is
Yeah.
the envelope at all interesting? It's not really part of the star, so to speak. It's just some tenuous atmosphere above it. So I don't get this.
Well, I think it's interesting because it can be disrupted, and it can be disrupted quite quickly and easily, and it's just hydrogen, which is kind of interesting.
Tiny amount of mass.
It's a tiny amount of mass, yes.
So you're going to
Yeah,
that it's going to have a signature.
Yeah, so even when you just disrupt the envelope, you get a signature. It's obviously much smaller than when you disrupt the core and the envelope. But there is some structure there, yeah. Okay. And so what we get when we add in the helium white dwarfs is something like this. And so the enhancement here from the cold white dwarfs to the helium white dwarfs with hydrogen envelopes is due to this expansion in radius, so they're much more easily disrupted. And the reason this goes all the way back to here is that they can, of course, burn out and be more close to the cold white dwarfs. Okay. So I'll just say a few words about rates. We still need to do a lot of thinking about this, but I think there's an important distinction between the rate of disruptions and the rate of things that we can see, right? As for the rate of disruptions, I don't think it's entirely clear yet what fraction of white dwarfs are these helium white dwarfs, unless anyone knows. What we do know is that in simulations about 10% of disruptions are white dwarfs for black holes around this mass range. This is up for debate as well, depending on what you think about mass segregation and things like that. And then we also know that in binaries, so this is in binary systems, helium white dwarfs take up about half of all binaries. This is where both objects are helium white dwarf, and integrating, you get about half there. Yeah.
What's the role of the binary?
Sorry?
What's the role of the binary? Why can't we just consider this?
Right. So this is just constrained from kind of evolution models. So they're formed in binaries, right? We don't always see them in binaries. I'm just kind of showing you what we know. Really what we want is just the total fraction of helium white dwarfs.
Effectively, the vast majority of helium white dwarfs are in very short period binaries.
Yes. Okay.
Because of the thing. It means that all the disruptions that actually
Yes. Yeah. So
about binaries. And in the case where the companion is the main sequence,
mhm.
something like that, then it will be started before the helium white dwarf. We won't even see the helium white dwarf starting just in the back.
It depends on the tidal radius.
I really say the main sequence will be much larger than helium white dwarf.
Yes, but so if you're talking about a specific black hole, then the main sequence, yeah.
It depends on if the orbit is constant or not. Right? If it was not in that same orbit when it was on the main versus when it becomes a white dwarf. Performing a random walk doesn't do super fun.
Yeah, but the complex binaries is usually hard to be kept in the binary. So when we come to the message black hole, high radius of the message itself is much larger, so it will be started even before the helium white dwarf starts. So if you have a helium white dwarf, that's fine. You actually even raise your chances. Right? But if you have the main sequence, then
Yeah, it's
also nice
a different
disruption, but it will be fine.
it's a different picture. Yeah, yeah. So it can be much more exciting. So basically, from this, very hand wavily, maybe 1%, maybe 0.1% of all disruptions. Where it becomes a little bit more interesting is where we think about the rate of luminous flares or of prompt flares. So as I showed earlier with the kind of phase space TDE menu plot, main sequence stars are kind of ineffectively circularized in the range of mass of black hole masses that we're concerned with. And James showed this in his dark year paper, where it's a little hard it's impossible to see actually, for 10 to the 5 to 10 to the 6 black holes, most of the events are slowed, okay? And for 10 to the 6 to 10 to the 7, it's still a significant fraction. And then when this for main sequence stars. And then when you finally get up above 10 to the 7 is where the circularization is more prompt. Okay. Now I'll talk about the hydrodynamics that we've done. So we just plugged in a stellar evolution MESA profile, and we just ran one model. It was a 0.2 M-sun white dwarf with a helium core of 10 to the minus 3, or sorry, a hydrogen envelope of 10 to the minus 3, and the radius was about a factor of 2.5, that of the core. And we plug this right into Flash. Right now we're using a nested polytrope setup. We're just setting up using a full Helmholtz equation of state. We don't have amazing resolution, but it's enough to get a good picture of what's going on and run across parameter space fairly quickly.
So the radius of the hydrogen envelope?
Yeah. So this rate. So just in terms of absolute units, it's 0.05 M-sun is the total radius.
0.05.
Yeah.
Okay.
Yeah. And as you know, Flash runs in the frame of the star. And so this is the model we looked at here. I ran over two different black hole masses, but I'll just be showing you for 10 to the 5, because there's just kind of scaling from to 10 to the 6, and I run across a range of impact parameters. And this is what it looks like. So we have, as you know, a surviving core, a debris tail bound to the black hole, a debris tail bound to the star, as you disrupt the object. And the first thing we can look at is mass ejected versus the impact parameter. Okay? And so remember, the mass of the hydrogen envelope is really way down here. We can't even see it on this linear plot. And so it's only at about beta of 1 that we start disrupting the core, and at that point, it's fairly easily disrupted up to beta of 1.5. Yeah. Oh, okay. Thank you. This is the log scale of the same plot I just showed you. And here, we can start to differentiate where the envelope is. So the envelope is right there, and the core is here. So for these betas, we disrupt the envelope. And for betas greater than 1, we're getting into the core as well. Next thing we can look at is the fallback rate, right? dmdt is dmde by dEdt. And dmde is what we need the simulation for, right? So that's the spread in specific energies, which is what the reason we need to run the hydrodynamics in the first place. dEdt, as we know, is from Kepler's law here. So first looking at dmde, that might be really tough to see. Sorry for the colors. we have a few more. So this is for the beta is 0.5, and it just traces like this here. Okay? And as we increase in beta, you see that more and more, as you expect, more and more mass is less bound to the core, right? So as you know, mass in the middle here, sorry, energies in the middle here correspond to bound to the core, and these ones are least bound to the core, or sorry, this is most bound to the core and least bound to the core. So we ran right up to beta of 1.5. See this kind of distribution. And then using this with Kepler's law, we get the mass fallback rate, which looks something like this. So I've plotted here the m dot Eddington for 10 to the 5 black hole, and time here. So this is 10 to the 5 seconds, 10 to the 6, 10 to the 7. So this is about a day, and this is about 10 days. And so for beta 0.5, we see something like this. We're still below Eddington. Remember, beta 0.5 to 1 is we're just disrupting the envelope. Okay? And then once we get to beta 1 to 1.5, where we're getting into the core, we're a factor of 100 to 1,000 above Eddington. And this fits a t to the minus 5/3 pretty well here. We can then convert this into luminosities. Naively, I didn't even plot luminosity, I just plotted 0.1 m dot c squared here. Okay? And we see for the substantial betas, thank you, for the substantial betas, we have luminosities of around 10 to the 46 for this event. But you can get sub-Eddington if you're just disrupting the envelope, which I think is that, yeah. Okay. And the time to peak here for the mass fallback rate is, for here it's around 4 days, and here it's around 12 days. And then you can just naively fit this on to kind of transient map, and these guys lie somewhere around here. And this is just using a semi-major axis photosphere limited by the Eddington. So they do occupy a somewhat unique region of both black hole mass and of phase space. And as I mentioned before, if just the envelope is disrupted, then we will potentially just see hydrogen, which I'm not sure if anything else or many other things can do, which is interesting. But these things are prompt, and they can be super Eddington for months, as we saw. Thank you. Mm-hmm. So I wasn't being very rigorous about it. I was just saying for RP less than 5 RG. Yeah. Yeah, and then I also have a, if you'd like to see, I have a plot of where what the TD menu looks like for RP less than 10 RG. So depending on how prompt circularization we want. Yeah, go for it.
So when you define data, what do you use for the radius of the star? Do you use the full radius?
Right, so I was using the full radius of the star, yeah.
Sure.
Sure, yeah.
So is this is it true that the rising part of this fallback rate is more shallower than main sequence instruction?
So you're saying this rising here
Yeah.
is that I haven't compared yet? Yeah.
It seems
It seems so, yeah. Yeah.
I remember quite before simulations of word-line disruption.
Mm-hmm.
Even for large people, it was impossible to
Yes.
destroy the core
Yeah.
of the star. What is the difference?
So these are much more easily disrupted, and that's because they are deeper, I think. Yeah.
Even though the tail radius to destroy the whole star is smaller than for word-line, and that's why they cannot do it.
Yes, of course, yeah. You might wanna put that. Oh, this is mine.
Sorry. כמה זמן שלי? רגע. תן עוד רגע. Okay, so I'm Chagai Peretz from Technion, and thank you for the organizers for giving me the opportunity to speak here. And what I want to tell you about is a bit of different kind of tidal disruption events. Most of this conference is basically dealing with tidal disruption of stars or different kind of maybe compact white dwarfs by massive black holes, maybe intermediate mass black hole. I want to go to a very different regime of disruptions by stellar compact objects. So if you think about it, and I should mention my collaborators, Jamie Lombardi and Julie, it's actually a project started very long ago. Even doing my PhD, Tal was involved in some early stages of this. So you can think about that tidal disruptions could occur at very wide range of scales. And maybe the most well-known one is the Schumacher-Levy comet disrupted by Jupiter, for example. So again, we don't have to go only to massive black hole disrupting stars. We can think about other cases where we can have disruptions, and they could also produce very interesting transients, which are also tidal disruption events, just of a different kind. So disruptions by stellar compact objects, and these could be principal black holes, neutron stars, or white dwarfs. I will mostly focus on black holes and neutron stars, which masses, especially black holes, are typically larger than the masses of typical stars. And the tidal radius, the tidal disruption radius, is larger than the size of the radius of the stars. Okay? So these kind of disruptions have been hardly explored. People did discuss disruptions of white dwarfs, for example, by neutron stars or black holes. This was studied and was simulated, but not much was really done about disruption of stars, main sequence stars, or planets by these compact objects. So we try to I call these micro TDEs, in a sense because what's micro here, 10 to the minus 6, is the mass of the compact object. Okay, 10 solar mass or 1 solar mass for black holes or neutron stars. So these are micro in the sense of the disrupting object. And so what I try to do here is give a basic characterization, a first try at least, to characterize what kind of events would we have from these kind of micro TDEs. And of course, it's always nice to see some movies. So let's just show an example. Oops, sorry. Why is that? Not good. Sorry. Something bad has happened here. Okay, so we just go to the here. So let's take this example. So we have a main sequence solar mass stars coming by a stellar black hole of 10 solar mass. In this case, it's only a partial disruption. We also did simulations of impact parameter, which is smaller. And you can see that how it's disrupted. And in this case, the star survives. But part of the mass is, of course, accreted on the stellar black hole. Just for nicety, we can also show how it looks in terms of column density. It's a bit nicer with some specific inclination, and you can see these kind of events. Okay, so we can actually simulate it. It's actually probably simpler to simulate these kind of events than the case of disruption by massive black holes. What's going on here? Okay, sorry for all these problems. Yes. Okay. So in this case in this simulation, what I showed here is I'll answer two different things. One you didn't ask about. We had the disruption itself happens. The pericenter of the closed approach happens at about this case was about 2 solar radius, and the kind of full disruption happens at about 1.3 solar radius. Hence, compared to the gravitational to the Schwarzschild radius, for example, okay, this is order of magnitude larger, right? You're talking about it's of the order of a solar radius, okay, compared to I don't know the 10 kilometer or so for a black hole, or a bit larger for a neutron star. And it's more.
So for that, I'm a bit confused about the context. You're thinking about a planetary-like system where the primary, the star, already fell off the main sequence. It's now a compact object.
So okay, what I have here, I'll discuss the channels of having this later on. Okay, but I'll begin. What I have is a stellar compact object. Let's say a black hole, and you have another star coming by. Okay, at very close approach and being disrupted at the tidal radius. That's the basic scenario. How you get there? Okay, you have various different channels, and I'll talk about each one of them later on. That's of course related also to the rates and the kind of environments. What kind of progenitors do you have for these kind of objects? But let's begin with just the kind of simple-minded characterization. First of all, if you want to try to look on the fallback rate, so that of course depends on how on the close approach. And it's a bit different than for massive black hole, because in this case, the massive object is not much more massive than the disrupted object. So it's not like it's in the center of mass, they actually move around, and you have some differences. And if you look for kind of a full disruption, you see that this is a minus 5/3, but you can see that the actual fallback rate is a bit different. And it's actually even more different in the case where we take larger closest approaches, though it seems like this is for a case of 1.94 and 2.15 of Arsan, and they start to go for very specific kind of parallel evolution, but which is different from the minus 5/3.
Okay, yes. I mean, you're 12 orders above magnitude above Eddington, right, or something like that.
Yes,
12,
yes.
13, whatever. I mean, can you actually use this kind of analysis at all? I mean, let me ask you a very basic question. Do you know what would happen if you, without any tidal disruption, you just took a black hole and put it in the middle of the sun?
No, certainly. I would agree that this is going to be super Eddington. So so this is just a fallback now, kind of the form of fallback in terms of if you just look on the Keplerian fallback of this thing. Of course, you have a lot of radiation, so it's not very clear how much mass really is going to get accreted onto a black hole in the end. Okay, for example. So I don't think that's actually described the really fallback rate onto the massive black hole. More important is actually the typical time scale. It's about a few thousands of seconds in this case. But after this fallback, whatever happens there, of course, yeah, much of it might be just outflown and never actually get to the black hole. If you form some kind of, just before that, if you just, again, the fraction of bound material, even before talking about outflows, of course, depends on how close you are. And it could get to up to a few tens of percent of the star. And of course, it becomes smaller and smaller. And above, 2 or 3 times the entire radius, even these partial disruptions become really inefficient. Of course, and then you can ask about what happens next. Okay, so some of the material, of course, could form a disk around the black hole. Okay, it's like in some sense, like in a GLB scenario. But of course, the size of this disk is of the scale of the tidal disruption radius. So it's much, much larger, of course, and this relates to your question about how far is it from the Schwarzschild radius. And so the question is, of course, how much material would actually accrete to the black hole? Very naive scenario, okay? So, but anyway, the time scale for this accretion would be about a viscous time scale. And the viscous time scale would give us a few tens of thousands of seconds in principle. Of course, depends on the specific parameters. But it is a time scale which is a bit larger than the actual time scale for the fallback. So what would determine the time scale for this whole event would not be the fallback time scale in this case, but more likely the viscous time scale of the accretion onto the black hole. Now we can ask how much, what's the energy of this kind of flare? And that, of course, depends on how much mass is falling back to the massive black hole. The most naive case would say, okay, let's say take all the mass, which is actually bound, and you say it's accreted on the black hole. This is very naive and unlikely, of course, but this will give you kind of an upper bound of about 10 to the 52 ergs, something like that. If you try kind of a more, maybe more realistic scenario, you can think about various scenarios that people discuss for accretion disk about black holes. Actually, not many discuss very large scale accretion disk around the stellar black holes. So it's, I'm not sure about how it scales exactly, but if you use models by Narayan and PhD is also on that paper, then we can get, of course, that most of the material is not really accreted in the black hole. Only a very small fraction, which for tidal, for solar star, it gets about 10 to the minus 4, more or less, of the material. It's actually accreted in the black hole, and all the rest is actually outflown away. So the actual energy they expect is a few orders of magnitude smaller than the actual energy that you have in terms of the mass of the star. Okay, so what we characterize kind of basic characterization, and of course this is simple, and I agree. This whole aspect of when you have super Eddington case is difficult to really characterize. But in terms of the time scale, we expect of the order of 10 to the 4 seconds or so. In terms of the energetics following this kind of characterization, we get of the order of 10 to the minus 4 of the energy that we have for the full energy from a star disrupted. Now, what kind of how can we actually get these kind of events? So I can think of 3 major channels that we can consider. One of them is just close encounters in dense clusters. We have 2 stars randomly encountering each other. In other cases, we have a close binary. We have a star collapse in a co-collapse. You have a natal kick of a neutron star, and by chance, the compact object actually goes very close to the companion and disrupt it. And another is possible, a very wide binary where perturbation by field stars change the angular momentum of star. It's very similar to tidal disruption events in the around massive black hole. We have kind of a lost cone aspect. You have perturbation of the wide companion. By chance, it could actually go close enough to the black hole and be disrupted. So if you look a bit more details. So dense, the case of close encounter is the most likely, of course, in dense environment, global cluster, maybe young superclusters in star-forming galaxies. The densities there could be 10 to the 5, 10 to the 6 star per parsec cubed. And if you do them, in this case, right, you just both the star and the compact object just have random velocities in the cluster, and by chance that you could actually encounter. And this kind of calculation were done for a calculation of what the fraction of collisions in stars, what the fraction of formation of X-ray binaries through tidal capture. It's a very similar calculation, and you get of the order of 10 to the minus 6 such micro tidal disruption events per year per Milky Way-like galaxy. So kind of yes.
It's
also nuclear cluster. Yeah. I meant any kind of dense cluster, of course. In case of nuclear cluster, of course, the gravitational focusing is much smaller, so the densities are higher, but the focusing is smaller. So, and we have only one per galaxy, a global cluster also. So I think the dominant is still going to be global clusters, geometric clusters, but galactic nuclear clusters are also going to add to this calculation. So if you do this kind of basic calculation, you get about 10 to the minus 6 for black hole disruptions, and about 10 to the minus 7 for neutron stars. The most different effect is you have more neutron stars in clusters, potentially. Of course, that depends on the. This was taken for a retention function of about 5%. So only 5% of neutron star or black holes in the cluster are actually retained there. So you get about 10 to the minus 7 for neutron star, 10 to the minus 6 for black hole, and mostly because of the larger gravitational focusing for black holes.
Okay. You might be able to get an extra factor of 10 or so by considering 3-body encounter.
Yeah, so that was the next, thanks, but that was the next step. The next line would be that, of course, if they are in binaries, you have higher fraction, you could get a factor of a few even higher. Most of the actual collision in clusters are typically in binaries if the binary fraction is high enough. Of course, when you have neutron stars, the binary fraction might be small, so it depends, yes.
Yeah, there are actually a lot of calculations of this done quite a long time ago.
Of these, of course, yes.
You know, in particular, the binary third star encounter.
Yeah.
And the rate is going to be dominated by events in which the impact parameter of the third star is within a few separations of the binary. Because what happens then is that there's a very complicated interaction with the stars all kind of wind around each other many, many times. And because there's so many passages, the probability of one of them.
Yeah. So what you get, okay, in general, what you get, you have a binary single encounter. Okay, it's a chaotic encounter, and so you effectively each time you have a star going up and coming back. So in a sense, you have about a few tens of close encounters in each these binary single encounters, and each one of them has a chance. So you multiply your probability for regular star by the larger cross section of the binary. Okay, this gives you about 60 chance of doing that. But now, of course, you have to take into account that you only need a very close encounter in these of these chances. Overall, you get typically a factor of a few larger cases. That depends, of course, on the binary separation distribution, etc. But this is, I did this calculation. I know that some of the people who worked on these, I think, are in the audience. Yeah. Yes. So, yes. Okay, natal kicks. So we know that neutron stars have natal kicks. We see the pulsar velocity, which are very high. So we know that post-core collapse of supernova, you can get, for neutron stars, get very high velocity kicks. It is less known about black holes and what are their velocity. Do they have kick velocities? Are they just so-called momentum kicks, in the sense that they have the same amount of momentum as in neutron star kicks, because you actually have a collapse into a neutron star, then a neutron star collapses into a black hole. In this case, you might have natal kicks like neutron stars, but of course you have to, in terms of the velocity, you have to take into account the higher mass of the black hole. Thank you. So in this case, if you have some kind of some in orbit, and then you collapse and you get a kick. If by chance, the kicks actually give you a different orbit, it might be actually still be bound binary, but very eccentric, or very likely to become unbound, and just by chance, as it becomes unbound, it actually comes close to the star and disrupts it. The probability for this, it's much more difficult, much more complicated to estimate. Not in the sense once you know, of course, the kick, etc. It's just Keplerian physics, a bit nasty, but it's just two-body Keplerian physics. The question is what's the fraction, what's the distribution of closed binaries just before the disruption, and that depends on the not very complex binary cell evolution. So what we try to do there is kind of do a basic population synthesis analysis under various kind of conditions and see what's the overall rate that you get. This is still work in progress, so I can't give you the actual numbers for this.
You just mentioned that was the case that Brad Hansen and I like best for making the pulsar with planets around, and planets get made.
Being things. Thank you. So these are the kind of things, and many of the scenarios that I discussed here were discussed in some sense, especially for tidal capture or for different aspects. I'm just focusing on the disruption itself in the sense of what kind of transit we see and their rates. But certainly there was work done on, of course, on close encounters, huge amount of work. Of course, in this case, you don't have just a straight kick. You have also gravitational focusing, which affects it, and the probability could be a bit higher than that. what nice thing about this case is that you actually can, in some cases, get still a bound orbit, which is just eccentric. In this case, you can actually get disruption of an eccentric disruption, not a parabolic or hyperbolic. In this case, you can actually have even several kind of periodic or quasi-periodic tidal disruption event. Each time the star disrupts a bit more, and you might actually have these multiple events on the time scale of the size of the orbit, which will probably could be a few days, maybe most. Last possibility is actually talking about very wide binaries. Okay, I'm talking about larger than 10 to the 3 AU. In this case, these wide binaries in the field could be perturbed by flybys of stars. As the flyby of stars, each perturbation kind of gives a kick to the star, and the star can actually change its angular momentum in phase space, very similar to what you have in a massive black hole, and stars, perturbed ice stars, and relaxation processes in galactic nuclei. So the same process could actually give a star a very eccentric orbit, so such that it get over time to become eccentric enough and be disrupted by the companion. So this is actually another interesting way of actually getting low mass extra binaries in the field, which is a difficult problem by itself. How do you get actually low mass extra binaries, especially black hole low mass extra binaries? And this is one scenario where you can actually get it in the field. You don't need a dense environment like in cluster we have these strong encounters. You can even have this perturbation in the field. Calculation of this would give us about 10 to the minus 7 per year per Milky Way galaxy. That's the rates of these kind of disruption events. Okay, so right here you have a flyby changing the orbit, and now it becomes close enough to be disrupted. So if I try to summarize what do I get from these kind of micro-tidal disruption events, what we might expect is a very long, 10 to the 4 seconds or so, relatively faint in terms of energy compared to GRBs, but potentially very similar to GRB in terms of you have accretion of black hole, you might form a jet. Of course, this is not very well understood. And the amount of energy is just related to probably to the amount of mass which is accreted. So you get an ultra long and relatively faint kind of GRBs or X-ray flares. And this might be associated, might be related to the class of ultra long GRBs that was found in recent years, which have actually these kind of time scales. It might also be related to some very late flares that people saw in GRBs, which are also of the scale of about a few tens of thousands of seconds. For example, in GRB 05, 07, 09, we had a flare following the GRB. You have an X-ray flare about 16 days after the winter flare, which is very difficult to explain in terms of the internal engine operating so long after. But it might, you can think of a kick that disrupted later on disrupted a star or some kind of companion at this time scale of 16 days. Now, the kind of each one of the channels I discussed, of course, would have different prediction in terms of the environment that we see these kind of events. If you have, of course, dense clusters, this could be either globular clusters, so these would be old environments, but it could also be in nuclear clusters mentioned here, or in young supermassive clusters. But these would be kind of old environments, probably mostly in old environments. If you're talking about these natal kicks, this would be just following the core collapse. So this would be just only in very young environments, of course, okay, and not in old environments, only after the star formation and the core collapse. And if you're talking about these wide binaries, this could happen again all the time in principle in any kind of environments, generally in the field. Okay, so what I try to do here is just trying to tell you that micro-TDs might be really interesting new kind of transients that should be discussed in relation to future transient servers, and try to look at them in that aspect. And of course, there's a lot of work to be done still in terms of characterization. And of course, and there are some very difficult questions about how to model it, which I'm not really able to do this. As mentioned, the super Eddington aspect of how this disruption looks like in the end is still not well understood. So that's it mostly. These were parabolic. What I showed in the masses, these were parabolic. These were not eccentric ones.
But they become eccentric once they've had one pass on, right? Because they're slightly bound to the black hole afterwards because high rays on the star.
Yeah, but I also had one with the close approach, which is actually full tidal disruption, not the partial. So that was, even that one was not 5 to the third. Again, it was different than the farther one, which were partial. So.
It might just be interesting to consider that it's, to get the steeper slope, you kind of naturally reproduce that. Kimmy's 2012 paper shows that if you increase the eccentricity, the slope naturally gets steeper and steeper, and eventually it gets to a delta constant. So the question is, did you consider recombination transients from the unbound debris tail?
No, not yet. We haven't looked on the kind of all of this debris. We tried to start looking on how would the spectrum of debris look like, etc. Like you and other people did for the regular TDEs. But this is just again work in progress. I haven't shown this because it's and we have more uncertainties what we'll discuss in terms of super Eddington aspect of it. But yes, it's certainly a future thing to do.
But James, I mean, the T to the minus 5/3 only arises assuming essentially uniform distribution in energy, right? And here
it arises where you have flat parts of the DMD. So wherever it's flat will be T to the minus 5/3. And the reason why it's power law changes is because you take, for an eccentric disruption, you take the distribution and you shift it in energy. So the late time stuff has a slope steeper.
But here isn't the issue that even if you don't consider eccentricity, that because the size of the periapsis and the size of the star are essentially comparable, that you're no longer in this flat DMD regime?
Yeah, that's a possibility. That's why I was asking.
As I said, these were hyperbolic. These were parabolic. These were not eccentric ones. We also I showed one eccentric later on, but these are parabolic.
The T to the minus 1 5/3 will come always when you have any DMD around T equals 0, finite DMD. You don't need anything flat. You always approach.
Why? Because the derivative is
Because the factor in very late time comes from whatever is at T equals 0.
I guess you'll have.
You should have been in the first lecture.
No. I mean, you can asymptotically approach the slope that's non-zero, and you can have a point like basically cost it at zero energy.
Yes.
So at zero, you can have exactly 5/3, but just approaching zero, you can have slopes that are not 5/3. Right, but that corresponds to infinite time, right? So you're interested in not infinite time. Yeah,
For each factor of 2, you get closer and closer to the 0 point energy. The other slope, you get real as the power law, you're getting very close to 0.
It might be interesting to think about these rather than in the disk picture, because the densities or optical depths are so enormous, to think of this as building this orange jigsaw object around the star, or maybe with some angular momentum, maybe disky shape.
That's the way you might think about it as a deformity.
Maybe more about the diffusion and behavior of material rather than anything like information.
That's true, but I mean, initially it begins in dynamical time scale. These are so needed. I guess people talk about more longer time scale, and you get to some equilibrium.
But you dump the material on in a dynamical time scale, but
Yeah, I agree that then. It's true. The question, but one of the questions is whether it's even small part of it actually does accrete directly to the black hole, and if it does form a jet. I agree. So it's the same kind of problems or challenges for both cases. I agree. It's very strongly related to that issues.
We have one last question.
The context of the whole collapse supernova, I want just overlap the supernova. How can you get
Okay.
How can you get a significant time delay there? Either the star is headed into the
No. In this case, the time scale for the supernova would be much larger. I mean, the delay in terms of the disruption would just be a few days, and the core collapse would be much larger. So certainly that would be at the same time as the supernova itself doing that. Yeah.
at the same time.
Yeah.
Not be able to distinguish. It will be some kind of a signal which is overlapping.
Yeah. But if this would be an X-ray flare, okay, and the supernova would, so we have both the X-ray flare and supernova. So these are different things. Very similar to GLBs in some sense that are associated with supernovae.
But it's buried inside the supernova.
Yeah.
That's what I was saying. It will be buried inside the supernova at the time that the supernova is
Yeah.
big. So it will be just another power.
It'll be like a magnetar, short flash magnetar.
I'm not sure. I mean, again, if it's a few days, okay, no, the envelope is already, no, the ejecta is already much less dense. So in terms of if you have a jet, okay, it would be easy, you'd have an easy time to go through the full envelope. So it's a bit different in that sense. Okay, in that sense. Fine.
Okay,
I'm fine with my
for
difference.
coffee, and meet here back here at 10:15.
Let me show you what I was talking about.
Okay, when you get a second,
Okay.
if it's publishable,
Uh,
if it's okay, if not, remove whatever